Thank you. Good morning, everyone. So this morning we're going to talk about ensemble models and try to demystify it. So I just want to give you some pointers to start with. There will be quite a few, like a little bit of notebook today. So if you want to follow yourself, you have access to all the content on my GitHub. You've got the PDF and the notebook there, and a nice little script to download the data. Right. So it's Lemagnen, and then you have ODSC 2018. Right. So ensemble models. First, why? Yeah. That's too quick. Yeah. Yeah? Okay. Cool. So why am I even talking about ensemble models? Well, the main reason that I put as the first one here is that they give good performance. So that's what you want. We are building models, we're expecting them to give good performance. Ensemble provides you that. And they also work in a wide range of problems. So you can apply it on all sort of tabular data. They're usually easier to train than other fancy techniques, like they will require less data on usually than deep learning, and they will be faster to train. They're also really popular in the industry and in machine learning competitions. So if you're not using them yourself, it's quite likely that some of your colleagues are using them or your competitors are using them, so you should care about it. The way I wanted to structure this talk is to look at the theory behind ensemble models, give some intuition, try to give some pointers in why they work, how they work, the different parameters that you can use to constrain them. And on the other side, look at the implementation in Python that some of you might be using as a black box maybe, and try to build a bridge between those two. So I want to look into the black box here and see how we can relate that to the theory. So in order to do that, I'll start first by giving a quick introduction and some intuition about what we're trying to do with ensembles. Then I'll look at the main building block of ensemble models that we call weak learner. More on that later. And then two main principal methods that are used for ensembles, bagging and boosting. And at the end, I'll just introduce other boosting libraries, because there are quite a few out there. Right, so if we're good with that, first I have mentioned ensemble models, but I haven't really defined it. So what we're trying to do here is to combine multiple simple models that might not be great by themselves if you just look at them individually. So we'll call those models weak learners. And if you combine them all together, you're hoping to get better performance. And that larger model that is constituted of multiple simple models is called the ensemble. Here, just to give you a little bit of terminology, the simple model is called a weak learner. Usually, we'll use a decision tree, and we'll see in a minute why we're using decision trees. And we'll see two popular techniques, bagging and boosting. So we're answering two questions here. So we're saying we're combining multiple simple models in a bigger one. The question is, what do we ensemble? The answer to that is those weak learners that will be decision trees. Then how do we ensemble them? That's what bagging and boosting is, and we'll talk about it in a minute. Just a little bit of intuition. Why are we even doing that? Why are we bothering ensembling simple models together? Well, so let's take this problem. You have access to two doctors and you get all their records, and you're able to compute the accuracy of each of your each one of your doctors. The first one has 60% accuracy on past data on previous patients. The second one has 75% accuracy. Now, both of them tell you that you have, say, a disease called X. Here, what we are wondering is the likelihood that you actually have X, is it going to be lower than 60%, in between 60% and 75%, or is it going to be higher? The answer to this question is it's higher than 75%. And the reason behind that is because the likelihood of both of those models, of those doctors to be wrong at the same time is quite low. So this works only if we are following two big assumptions. The first one is your weak learner, your expert, your doctor, needs to be more right than wrong on average to be able to combine their diagnostics. They need to be not completely like misleading. The second assumption here, that is probably the biggest one, is that you need some diversity. You need those two doctors to make errors in different way, because you're expecting that if you combine more doctors together, or more experts, more weak learners, their errors will compensate. So here, that's where our analogy of doctors doesn't keep up, because most certainly those doctors went to med school and are all taking the same decisions in the same way by looking at your symptoms. But here, that's something really important to keep in mind when we're building ensembles. We want to make our models diverse, so they make different errors, so those errors compensate. Right, so with that in mind, and remember those two properties for later, because that's going to come back through this talk a lot. Right, so our first building block here is the weak learner. So we'll, as I've said earlier, we'll use decision trees. Why do we use decision trees? Well, they actually fit pretty well with those two properties that we need. They can capture quite complex relationships. They can map nonlinear relationship in your data. So they're pretty good at getting a more than average prediction. So you'll be able to build quite strong single models. And the second thing is that they overfit easily. Usually, having a model that overfits is seen as quite bad. But here, for our ensembles, it's a good thing, because that means that if we just introduce a little bit of noise in our data, we'll be able to artificially make our trees quite different. And we can use that to create diverse models that we'll be able to combine. Right, so now we know why we're using trees, but it's important to know how we can control them to make sure that they still work pretty well. So if you don't have any constraints on your trees, what it will do is just keep building and splitting your data into binary rules until you have one leaf per sample. And that's a massive overfitting. It will end up getting a decision path for every single sample you have in your data. So it's really important to put constraints on them still and to adjust them accordingly. So here there will be different ways to do it. There are different constraints that you can add on your algorithm. We'll see mostly two main constraints here. The first one is picking a maximum depth. So you're saying after a certain depth, you stop building binary rules in your trees. The second one is the minimum number of samples that you need to justify a new split. And we'll see that in a minute in the notebook. But it's important to control the depth of your tree. So let's open the notebook here and see how that works in practice with the Python implementation in scikit-learn. So First here I'm importing a few plotting libraries. You see that I've cheated a little bit and I've created some helpers functions because I don't want to write all the matplotlib stuff every time. Quickly, a word on the data I'm using. It's some data provided by Facebook on how on like some characteristics of posts that were posted on different pages on Facebook. We have information about the category of the page that that post was posted on. The post was posted on. We have the number of comments on the page, number of likes, all those kind of information. The targets, what we are going to predict here is a regression. It's the number of comments a post will have in the next hour. So that's the problem I'm setting here. Let's just have a quick look at the data. You see that the features are actually not really meaningful here. We could look it up, but it doesn't matter so much for our problem. We're using that as just a toy example. Here, x54 is our target. That's the number of comments a post will have in the next hour. We can just quickly look at how much data we have, 40,000 rows, so we have plenty to work with. Let's just extract from that our x and our y, and we're good to go. One last thing is that we'll split the data into the training set and the test data set, so we're able to go through that and evaluate our models later. So once I've done that, I'm able to start looking at decision trees. So decision trees with scikit-learn can be imported from the subpackage tree. Here we are working with a regression, so let's get the decision tree regressor. We'll start with just adding this constraint of max depth equal 2. So we have really, really constrained trees here. We'll be able to have only a maximum of 3 binary rules. And in fact, we can visualize it. Once I've trained the tree on my training set, I'm running this helper here that I've wrote. And I have all my binary rules, so only 3. Just to give a quick introduction, if you're not familiar with this visualization, you've got the name of your feature. So the first row in each of the cells is the binary rule that you're looking at. So we're focusing on feature number 30, and we're looking at whether or not it's smaller than 168. If you'd look at the mapping of the indexes of the feature with the actual meaning, I think x30 was the number of likes a post got on the page. The number of samples is quite interesting. It's how many, what's the ratio of the data set that is represented in this node by this binary rule. So here, if we see that at the top, of course, all the data set is represented. Then when we start going down, on the left, we have 97% of the data set that is concerned by this rule, and here 3% on the right. And that will come handy later when we're debugging our trees. And we see at the end we are predicting the final score. So we can also evaluate our model with here we've chosen to use the mean absolute error as a metric. So let's just look at it. The reason why I've chosen that is because it will be in the same unit as what we're trying to predict, so it's quite easy to interpret. Here, if I've got 7.7, that means that on average, I'm wrong by 7 posts when I'm trying to 7 comments when I'm trying to predict the number of comments a post will have. So it's quite useful. Right. So now we've trained a tree with a really big constraint on the max depth, and that gives us a really trivial model that surely isn't complex enough to model the relationship, the true relationship that we have in our data between x and y. So we'll try to increase the depth, and let's say we go for 12 here. Visualize it. And here we have this really, really complex tree. And in fact, here those gray squares mean we just can't visualize it. It goes too deep. But by looking a little bit closer, we see that we have nodes that are only representative of 0.0% of the data. So that surely looks like we're overfitting to some samples. Here, we're not even quite deep in the tree, and we're already building nodes that aren't representative of a large amount of data. So that's where we need a new parameter. Using the depth only is not enough to control our tree. We can make more complex trees, but then they will overfit to some amount of data, to some samples in the data. Let's look at the mean absolute error anyway. We've got 5.30, we've improved it, but surely we can do better if we can control this overfitting. So here, that's where the next parameter comes handy, the mean sample split. So we'll control exactly what you see here, the number of samples that we want to justify a node. So here, if I specify, for example, that my mean sample split should be 0.02, that means that I want to create nodes only if it's representative of at least 2% of the data. And I can run that, and you see that I've managed to build a tree that is deep enough to represent complex relationship, but also when I'm starting to overfit and have only little data represented in a node, I just stop. And that's the case here, for example, where you see the X34. Right, so if we check the mean absolute error of this tree, we see that we're actually doing better. That means our tree is generalizing better than our previous one. And that's what we wanted. So here the takeaway is really remember those two parameters. We're going to use them a lot when we are building our ensembles as well to control the complexity of our trees. So let's go back here. Now we've seen our main building block, the weak learner, the decision tree. Now we can see how we'll start ensembling those objects together. So the question is how we end up building diverse enough trees so that we can leverage that concept that we've seen above of an ensemble. So the first thing we can do is, instead of training all the trees on the same data set, we're going to build a new data set from scratch by subsampling from the initial one. We actually build a new data set with the same number of rows, but we sample with replacement from the original data set, which means that we have new data is statistically similar, but some of the observations will be there twice or three times. Some observations won't be there at all. And that's what we call bootstrapping. Another thing that we can do is do the same on the columns. So instead of providing all the trees with all the columns that you have here in your data set, we can choose to pick some columns at random and force your trees to learn from different features. So that will make them quite diverse. And the last point is really important. You need your trees. You need to let your trees overfit to the data. Say if you keep the max depth equal to, like we did initially, your trees are just going to learn really basic relationship, like the most basic it can get from the data set. So adding all this noise in the data is not going to change anything. Your trees will learn really simple rules that are true for whatever subset of the data you look at. So it's important here to loosen your constraints and make your trees overfit a little. Don't overdo it though. It's important for each tree individually to be good enough in making predictions. You don't want to have them underfit, and it's also important on the other side to be able to generalize, so not overfitting too much. So as usual, that's a trade-off that you need to find. And here is a diagram of that technique. So we start from X and Y. For each of the decision trees, here we have 3. We'll build a new data set by bootstrapping, so sampling with replacement from the original data set. Then we do features subsampling, so we select only at random a few features, and then we train each of our decision trees, and we aggregate everything together. Some pros and cons. this algorithm is pretty good in terms of implementation because you can run everything in parallel here. From building the data sets to training the decision trees, everything can be run on a different CPU on your computer, so that makes it quite fast to train. Also, we're using decision trees, so if you're familiar with decision trees, you'll know that you can get the feature importance from it by looking at how many times or how much impurity each feature is helping decreasing when building the tree. So when you have several trees, you can also do that and get importance of each of your features. An issue, though, is that even though we're doing all those steps in order to remove correlations between your trees, they still train on really similar data. It's still the same data set that you had initially. So your models will remain sort of correlated. You will never have that big boost that you would have if models would be completely independent. They're also harder to interpret than your original than a single tree, because here you're combining several of them. So you can't go down the hierarchy of one tree and just explain your decisions, your predictions. You'll need to look at all the trees together and then take the average. And another one that can be good or bad is how it deals with outliers. So since we are building new data sets by sampling data randomly, if you have outliers, if you have some elements that are really different and are like only one occurrence in your data set, they might be present only in one or just a few of the data frames. So only some of your trees will ever see this outlier, meaning that they kind of will be implicitly hidden from most of your other trees, which is usually a good thing. You don't want outliers to have too much of an impact on your model, but that's something to keep in mind. Right. So with that in mind, are we ready to take a look at how that's implemented with scikit-learn and how we can control that with Python? So the random forest can be imported from the Ensemble sub-package. We have a regressor version of it here that we can import. Here, just to explain a little bit the parameters, the second row here is the parameters that control your ensemble, the way your ensemble is built. So we define the number of trees we want to build. Here we'll start with 15. We define max features, which corresponds to the number of features you want to sample in your feature sub-sampling step. We also have the bootstrap parameter, which defines whether or not you want to do bootstrap, so we can completely deactivate it to start with, just to see how that will impact our model. And then you have those parameters that will constrain every single tree that you're building, the max depth and the mean sample split that we've seen already. Here you see that we are keeping our trees quite constrained, so we have a max depth of 5, meaning that our trees will be quite simple. And most importantly, we have a mean sample split of 0.1, so that means 10%. It will just create really, really simple trees here. So let's see how that goes. We'll fit it on our training data, compute the mean absolute error, and we get 6.4. Now, something really interesting with the implementation in scikit-learn is that you have access to every single decision tree that was built with the attribute estimators. So here I've got the list of all my single trees that are themselves scikit-learn decision tree objects. So I'll be able to access every tree and debug by checking for example, the accuracy of all those trees. Say I'm taking the first one here, and I can get the mean absolute error. But if I can do that, I can also do it for all my trees together. And here you're starting seeing something. All my trees have exactly the same accuracy, the same mean absolute error. If I then plot that with a custom function that I have imported from the helpers. If you're interested, by the way, I have it on GitHub in the helpers file. Here you'll see on the x-axis is the index of all the trees. So here we have our 15 trees and the mean absolute error for each of them. Here they all have the exact same mean absolute error, and in the red you have what you get from your random forest. So here, having the random forest, having our ensemble didn't give us any sort of advantage. We would have been the exact same MAE, but by using one single tree. And just to prove that we've built several times, 15 times the same tree, I've got this function that plots for a few samples the distribution of predictions. So say we are looking at this sample here, 4155. I'm plotting the distribution of predictions for this sample for all my 15 trees. So here all the 15 trees have predicted exactly the same value, 5. And I can see that for all those samples that I've selected, all my trees predicted the exact same value. So they are basically the same tree. They've learned the exact same thing from the data. So surely we don't want to do that. Now we'll change the parameters that control our ensemble to include bootstrap first and to include the feature subsampling. Here, if I define it as being auto, the random forest regressor will choose automatically what's the best number of features to sample from my data set. I keep the same values for my to control my trees to start with, and I'll take a look. So the mean absolute error has decreased a little bit. Let's look again at our plot. So we see here my 15 trees, and I spot that they have a different mean absolute error. And something interesting to notice is that the error of the random forest itself is lower than the best single tree that you have here. So that means we managed to benefit from this effect that we've seen at the beginning. By ensembling all those trees together, the the performance of the ensemble is better than your best tree. And we can look at how diverse they are by observing their predictions on different observations. So here we see, for example, this observation here, the median value predicted by our 15 trees is about 23, 24. But some of the trees, maybe one of our 15 trees will predict something up to 35. One other tree will have a really low prediction. So here we see that those trees, some of them will make mistakes, but sometimes it will be like over-predicting it, sometimes it will be under-predicting it, and we hope that on average we'll get closer to our target. And we see that it's pretty much the same for all our samples here. It's a bit harder to see for those ones because of the scale, this one being too high, but it's surely the same thing happening. Right, so now that we able to benefit from these advantages of ensembles, the next step, if you remember, so now we've used Bootstrap, we've used the feature subsampling, but we haven't loosened the constraints on our single tree. So we could get even better, surely, if we were able to let our trees overfit a little bit. So here I've changed the max depth to 15, giving a little bit more flexibility to my trees, and I'm most importantly changing this mean sample split so that trees can build a node even if it's representative of only a small sample of the data. So let's see what I get here as a mean absolute error. 4.05, I've improved it a lot by just decreasing the constraints that I have on my tree by losing it, and let my trees overfitting. Right, so let's check again what we have here. So you see here that your trees, if you look at every single tree, we haven't necessarily improved the accuracy of a single tree that much, but what we've increased is the diversity of our trees. So now, when we look at the performance of the ensemble compared to the best tree, we're quite much better than the best tree. The best tree is probably this one, index number 1, and we're quite below that in terms of a performance of our ensemble. So that's surely what we want. Now, if we look again at this plot, it shows how diverse our predictions are, and we again we managed to make them quite diverse. Right. So let's go back to the slides and see the next method, which is boosting. So here, until then, we've just built all our trees on data sets built by sampling at random, and we're hoping that if we have enough of those trees and we group them together, we're hoping that we'll make our performance better and that their errors will compensate. The question we're asking here with boosting is there a way, instead of just hoping that enough trees will have their errors compensate, is there a way we could actively build trees that actively compensate the error of the previous ones? And that's what boosting is trying to do. So to explain boosting, probably the easiest is to focus on one single sample. So if we take one single row xy, let's say that y is equal to 100 to start with. So for boosting, we'll build a first decision tree on our x and our y. So that tree will be looking at x and trying to predict this 100 here. Obviously, our tree is not perfect, and it will predict, say, 95. Then the next step is to compute the residual. So we check how far we were from what we were supposed to predict in the first time here. The difference is 5, and that's where boosting becomes interesting. We train our following tree, the decision tree 2, not on x and y anymore, but we train it on x and the residuals. We are making it actively trying to compensate for the error of the previous one. And then when we aggregate together our decision tree 1 and our decision tree 2, you notice that we've managed to get closer to that value 100 of y that we had initially. And then we repeat that. We still have a residual of 1 here, so we could train another tree that will try to compensate that and get again closer to the truth. So what we notice here is that our weak learners are increasingly focusing on the hard points in your data. You have to imagine that y will actually be a vector of points, and there will be some points that we will get right from the beginning and we'll get close to 0 in terms of residuals. Then other points that will get really wrong. And for those points, the residuals will be either really high if we've predicted it, or it will be really negative if we've overpredicted it. So that's what your second and your sequential decision trees will try to compensate for. Something to keep in mind here is that we could, since our decision trees are quite performant individually, we could have built a tree that overfits a lot and gets all the samples right in the first iteration, but that would overfit exactly to all the samples in your data. Instead, what you want to do is build the first tree that is getting kind of the overall, the easy rules that you can spot in your data, then focus only on those hard points that the first model couldn't get, and build another really simple model that is not going to overfit by itself to learn what's the overall pattern of what you have remaining in your errors. Here, something that you can anticipate is that it will overfit really easily, and that's probably one of the biggest problems with gradient boosting, is that if you have too many stages, or if your trees are too complex, if DT1 is too complex and predicts already all the values right, or if you have too many decision trees, you'll overfit to noise in your data. So it's really sensitive to that. Thus, getting the number of stages is extremely important here. And that's something you'll need to spend a lot of time working on, trying to check the different number of stages and getting that number right. Otherwise, you'll overfit. And you also need to build small and constrained trees. So here we're not in the same configuration as the random forest, where you were building trees that overfit and hoping that they will catch something different in the data and then compensate the error of each other. Here, every tree is actively compensating the error of the previous one, so you need to make them small enough that they correct only a small amount of error every time. And in fact, there is another parameter that I'm not mentioning here in the slides that is called the learning rate, that allows you to add a weight to every tree you're adding so that it corrects, it's limited to only a small amount of error it can correct. And here we have a diagram of how gradient boosting works. So we start with X and Y. We are building our first decision tree on X and Y as usual. But the second decision tree will be trained on the residuals of the first one, together with X. Then we compute again the residuals of our two first decision trees together, and we train a new one on it, and we aggregate everything together. Some pros and cons again. They usually give great performance, so gradient boosting is used a lot in the industry and in machine learning competitions. On Kaggle, for example, a lot of winning models will be using some XGBoost models. They also have that nice feature importance since they're using decision trees in under the hood. An issue is that since all the trees are built in parallel, they are built sequentially. It's harder to parallelize the algorithm. In fact, you can still have some optimizations and build the single trees in parallel, so just have the different nodes built on different CPUs, but you need to wait for one tree to complete before being able to train the second tree. They're also hard to interpret. Here, from your second tree, you're not even looking at your initial X and Y anymore, so your trees are your following trees are usually meaningless. And they can easily overfit, and it's probably the biggest con here. So let's do that in a notebook with scikit-learn. Right, so scikit-learn has an implementation of the gradient boosting algorithm. You can import here. Here we see our Ensemble parameters, so we have the number of estimators. We keep it low for now, because we don't want to overfit. See that it has those two features again, subsample and max features that we've seen before for random forest. And I haven't mentioned it, but we can enforce the diversity of trees as well. We can enforce and making sure that the second decision tree we're building will spot something differently in the data by doing the same features subsampling and the same row subsampling, so that your model only sees different points in the data and different features, and so learn something different. And here we have a learning rate that I mentioned earlier that allows you to add some weight and minimize the overfitting. Here you see that we've made our tree quite deep, but we're constraining them with having the mean sample split of 5%. Right, so let's take a look at what sort of performance we get with that. 5.12, right? So here, unfortunately, we can't, I mean, we looking at the mean absolute error per tree alone wouldn't make any sense, because the second, from the second tree, we're training them on the residual. So they were never meant to be accurate on your initial Y. But what scikit-learn allows you to do is to generate predictions as if you were including only up to, say, tree 3 or tree 4 in your data. So if you iterate over the stage predict, what the stage predict method returns, you'll get a prediction for tree 1 and 2 together, tree 1, 2, 3 together, and we have the list here, and we see how the mean absolute error decreases when you're adding more trees. And we can visualize that, as we've done before, looking at stage 1 here up to stage 5, and we kept decreasing the error. Something that can be interesting as well is to look at the residuals in your data. So here, at different stage, the residuals on the training data decreased and went towards 0. So we see that initially we've over predicted the values, and by adding more stages, we're correcting that error and getting towards 0. So now let's modify that and try to use more trees, because if you look at this plot, you see that we kept decreasing the error, but we might have been able to do more by adding more trees. It seemed like it was converging to something. So let's take a look at that. And here we see something interesting. So up to, say, stage 5, we've decreased the error by adding more trees, but then after a while, we stopped improving anything in our model. And if we look at the residuals, it's the same idea here. Up to stage 5, we started stabilizing. So surely here, adding more trees is not the solution anymore. We won't be able to improve our error by doing that. What we need to do instead is loosen the constraints on our tree so we can pick more complex relationship. We've reached a stage where our trees are not able to even capture that error in the data. So here I've changed the depth and the mean sample split to 0.1%, and let's see how that one goes. So takes seconds, 4.9, we've improved our overall mean square error, and here we see something interesting by letting our trees overfit too much. So I've done that on purpose here to have a really loose constraint on my mean sample split. I've actually decreased the mean absolute error up to 4, but then I started overfitting to noise, and that's what you can see here. My models are too complex, my trees are too complex, and after a while they just end up capturing the noise in the data. So here I've done it, I've loosened the constraints too much. So let's take a look at the residuals as well. It shows us the same thing. So for our final model, we know that the mean, we need to constrain our tree a little bit more than we've done here, and that's what I'm going to try here with a mean sample split of 0.5% instead of 0.1. And I see that I've increased my overall mean squared error, and if I look, that's the kind of mean square error chart that I want to look at, that I want to see. So here I've properly converged towards a good value, and I stopped adding more trees when it started to converge and stabilize. If we look at the residuals, it tells us the same story. We've nicely decreased the error up to a certain point, and then we've stopped adding more trees before overfitting. Just a quick introduction to other libraries. So here we've seen the implementation of gradient boosting in scikit-learn. In fact, there are many other libraries that offer implementation and claim that they are either more performant in terms of scores you get from it or in terms of how fast they train. So here I'm going to take a look at XGBoost, LightGBM, and CatBoost and just run them. It's not a fair comparison here because I haven't tuned all the models, but I just want to show that you're able to get the models with the exact same API we had for scikit-learn and do the .fit, .predict, and then compute your mean absolute error. So you could easily include those other libraries into your analysis if you wanted. So let's train a XGBoost regressor, and I get actually a pretty good accuracy with the default parameters here, a LightGBM and a CatBoost. Yeah. Right. So that's it for me. Do you have any questions? Yep.
Why is the constraint of 50% accuracy in the trees? Surely there's some sort of trade-off between the correlation and the accuracy. They'll lower that to make sure the correlation.
Why is the constraint of 50% for the mean sample split?
In the very beginning, when I was talking about the selection of the trees, you basically talking about each one having an accuracy of at least 50%. So, the very beginning.
Oh, in the slides, you mean?
Yeah.
Yeah. Yeah. So we need our trees to be to truly benefit from it. We need our single trees to be good enough. Like there is a limit on how if you ensemble really bad models, you won't manage to get a satisfying accuracy unless they by themselves are good enough. So. Yeah, in theory, but in practice, there is a certain number of trees that you can build with a correlation that is small enough. So after a while, when you keep adding trees, to control the correlation. So that's what the subsampling is doing, trying to limit the correlation between your trees. But that's the thing, if you add too much noise in your data set in order to have less correlations, then you'll make trees less good after a while. So there's a trade-off to find here, where you want to make your data set noisy enough so your trees capture different things, but not too noisy so that they still remain performant by themselves on their own. Yeah. Other questions? Yeah.
So how does feature importance work across the previous trees? How does the feature importance of all the ensemble compare to each individual?
So the question is how feature importance works when we have multiple trees. So it's aggregating the feature importance as well. It knows each tree gives you a score for the feature importance. So when you add them together, for the random forest, all the trees are added together with the same weight, so it's quite easy to get the feature importance. For boosting, it's more complicated because the feature importance, surely you would need to give a different weight depending on which stage you are. Like the first stage is where it's the only one that has actually seen the true data. So the first stage you have more weight on its features importance, but it actually depends on the implementation. I think XGBoost is actually not properly weighting and I need to double check that, but it's not properly weighting the different trees. So the feature importance by default that is written by XGBoost, I wouldn't really trust it. So different implementations will have their own way of aggregating that. Yeah. Sorry, I didn't hear.
Class and balance better.
Which will handle what?
Class and balance, sorry. Number of positive samples and negative samples.
Classification.
Yeah.
Between boosting and random forest. Well, I don't think there is an answer to that. Like they both can work pretty well. Yeah, it will depend on the actual data you have and how. Like usually, you should be able to, if you properly tune your boosting, your XG boost, you should get better performance just empirically, but there is no guarantee. It depends on your data. Yeah. More questions? Yeah.
Ensemble is completely new for me. I would like to know whether this can be applied for all three types of learning, supervised, unsupervised, and also reinforcement learning.
To apply it for unsupervised learning? Well, not that I know of. How would you do that?
Models, when they say models, I was thinking, is it only for...
Because they need labels. They need to be trained on labels, so you can't really.
So only supervised?
Yeah. Well, as far as I know, yeah. Yeah. Yeah.
XG there is for minimum child weight.
Say again. Sorry.
XG
Yeah.
minimum child weight.
Yeah. Minimum child weight. It's similar to tuning your mean sample split. It's just saying when you're creating a new child node, how much weight that child should have, and the weight is defined as well, by default it will be 1 for every sample, but you can override that if you want it. So that's particularly useful if you have a classification problem and you have imbalanced data. For example, you can give more weight to some class, in which case, when you're using this parameter, you can refer to those weights and say that I need at least this equivalent of weight to create a new node. So that's a way to avoid overfitting as well. It's going to be equivalent to a mean sample split, but it's applying that constraint differently. Yeah. Ooh, so many questions. Yeah.
I'm new to the topic, but just a thought. What if you build a random forest and then try to correct the error of this random forest by another random forest? Boosting, but instead of trees forests.
Using boosting on random forest. Yeah, you could do that. So you've got, I don't know if there is a way to do boosting per se, but you've got, on scikit-learn there is a stacking class, a stacking tool that allows you to build a meta model out of other models such as random forest or XGBoost and group them together. No, so pipeline is used to go sequentially. So you have all your pre-processing steps in the data, then you're training your model, and you get a result out of it. That's the pipeline. The stacking is having several models in parallel that you aggregate in a way, and you have all the flexibility you want to train the models you want, and then aggregate them. So that means that there you could stack together several random forests, several XGBoost or whatever you want really, and then aggregate them. Yeah?
So the question on stacking, is there any research into different types of models for each learner? So we're using decision trees here. Would you ever use any other models?
For bagging? So in practice, it's pretty much always decision trees. I've never had to use another model. Now, if you wanted to try with other, because decision trees work really well because they overfit easily and they're really unstable models. Now, if you wanted to use another model and try it, you could do that with scikit-learn. I think if you go to sklearn ensemble import, yeah, they have that bagging regressor that allows you to apply that idea of bagging, ensembling with any model you want. Yeah. So yeah, categorical variables is a bit annoying with scikit-learn because even though in theory decision trees should support it, in scikit-learn the implementation is expecting numbers. And the problem is that if you add integer labels instead of your initial categories, it won't recognize it as being categories, but it will think that there is an ordering there. So you can't do that either. You would have to use dummies in this case, one-hot encoding. CatBoost, though, has a pretty clever way of handling the categorical features by default, so that that could be something to look at if you want to train a model with categorical features without building one-hot encoded features. Yeah.
If you only have extremely weak learners, accuracy is just above 50%. Is it still worth doing this in your experience, or is there actually a practical limit that's slightly?
So if you have extremely deep trees, extremely weak learners. So meaning that they have a really low score. Well, so the problem here is that it would you would benefit from the a big improvement only if you were able to build really decorrelated models, and a lot of them, and that's usually the hardest part because you have only one data set that you're using. So all of your extremely weak learners will see this really similar data, even though you're using those tricks to add noise. Yeah, I'm told to stop. Sorry.
Actually,
Right.
since the
Thank you very much.